Introduction. Ravi's mother is pouring the detergent powder into the water bucket and start shaking well by hands. Due to this, they have produced a lot of soap bubbles and are coming out from the bucket. Ravi, watching this curiously, and asked his mother that why soap bubbles are stable while water bubbles are not. His mother replied him that it happened due to the surface tension. When detergent is added to the water, then the surface tension is decreased. Hence, a lot of stable bubbles are produced. Students, you must want to know more about this. Today, we will study about the fluids and their mechanical properties. Objectives. At the end of this lesson, you will be able to define fluids, calculate pressure, describe hydrostatic and atmospheric pressure, define streamline flow, analyze equation of continuity, know Bernoulli's principle and Torrecelli's law, define viscosity, analyze Stokes' law and Reynolds number, define surface tension, calculate surface energy and angle of contact, know about phenomena based on surface tension. Definition. A fluid is a substance that can flow. So, the term fluid includes both liquids and gases. Since fluids change their shape rapidly, therefore, their mechanical behavior cannot be described in the same manner as in case of solids. There are marked differences between liquids and gases. For example, gases are easily compressed, whereas liquid are nearly incompressible. Liquid has definite size, but a gas expands to fill any closed vessel containing it. Hydrostatic and atmospheric pressure. Hydrostatic pressure is defined as the pressure exerted by a liquid at rest. Consider a liquid of density D filled in a vessel up to a height h. Then, pressure exerted by the liquid on the base is given by P is equal to HdG. The expression shows that the hydrostatic pressure depends on the vertical height of the liquid and density of the liquid. Atmospheric pressure. The pressure exerted by the atmosphere is called atmospheric pressure. The device used to measure the atmospheric pressure is called barometer. 1 atmospheric pressure is equal to pressure exerted by 76 centimeter of mercury, or 1 atom is equal to 1.013 into 10 raised to the power 5 Newton meter per square. If the atmosphere is assumed as air of uniform density 1.3 kilogram meter per cube, then height of the atmosphere is equivalent to 7.95 kilometer. Streamline flow. A flow is said to be steady if the fluid velocity at a point does not change with time, and the statement holds for all the points. A streamline is a line drawn such that at each point its direction is the direction of the fluid velocity at that point. In a steady flow, streamlines are stationary and they do not cut each other. If they cut each other, then we say that the flow is turbulent. Equation of continuity. Rate of flow of a fluid through a cross-section A is given by V is equal to AV, where V is equal to velocity of the fluid and capital V is equal to volume of the fluid. If the pipe size varies, then flow velocity also varies. Now, rate of flow is given by V is equal to A1V1 is equal to A1V2. This equation is known as the equation of continuity. It shows that where the tube area is large, speed is low, and where the tube area is small, speed is high. Bernoulli's principle. Bernoulli's theorem states that when An ideal fluid flows in a streamlined motion from one point to another. Then, at every point of its path, the total energy per unit volume remains constant. Let an ideal fluid element of mass m flowing in a pipe of varying cross-section. The fluid in a section of length v1 delta t moves to the section of length v2 delta t in time delta t. The density of fluid is rho. Then, according to Bernoulli's theorem, sum of kinetic energy, potential energy and pressure energy at point 1 is equal to sum of kinetic energy, potential energy and pressure energy at point 2. Torricelli's law. Torricelli's theorem states that the speed through which a liquid is discharged through a small hole at a certain depth is the same as the speed of a body falling from rest from an equal height. Speed of the liquid is given by V is equal to under root 2 gh, where h is equal to initial level of liquid, g is equal to gravity constant. Viscosity. It is defined as the property of a liquid by virtue of which an internal resistance comes into play, which tries to destroy the relative motion between the layers. This internal resistance acts tangentially on the layers of the liquid. Newton's law of viscous force states that viscous force between the two layers of a liquid is directly proportional to the area of the two layers in contact and velocity gradient between the layers. F is directly proportional to A into delta V upon delta X. This equation can be written as F is equal to minus eta A into delta V upon delta X, where eta is equal to coefficient of viscosity of the liquid, and the negative sign shows that the viscous force is directed opposite to the motion of the liquid. Its dimensional formula is ml to the power minus 1 t to the power minus 1. Stokes' law. Stokes' law states that when a spherical body moves inside a viscous fluid, it experiences a force on it in the direction opposite to its motion due to the viscosity of the fluid. The opposing force is called viscous force. This force at a particular instant depends on the coefficient of viscosity of the medium, the radius of the spherical body, the velocity of the spherical body at that instant. Force is directly proportional to eta, radius and velocity. On summarizing all the above equations, we get the result. F is equal to 6 pi into eta into r into v. Example. Let's take an example on Stokes' law. A raindrop of radius 1 mm has terminal velocity of 2.4 meter per second in air. Calculate the viscous force on the raindrop. If eta for air is 2 into 10 raised to the power minus 4 poise. Let's see the solution. Given values are r is equal to 1 millimeter, which can be written as 0.1 centimeter. V is equal to 2.4 into 10 square centimeter per second. Eta is equal to 2 into 10 raised to the power minus 4 poise. We know that F is equal to 6 pi eta RV. Putting their respective values in the above equation, on calculating we get F is equal to 9.05 into 10 raised to the power minus 2 dyne, which is equal to 0.091 dyne. Hence, the viscous force on air drop is 0.091 dyne. Reynolds number. Critical velocity is the maximum value of velocity up to which the flow of liquid remains streamlined. The value of critical velocity Vc for a liquid flowing in a tube is equal to K into eta upon rho into alpha. This relationship is known as Reynolds formula. Here, eta is equal to the coefficient of viscosity, rho is equal to density of the liquid, alpha is equal to radius of the tube, K is equal to Reynolds number. Reynolds number K is a dimensionless constant. From the above relation, it is observed that for a non-viscous liquid, the flow will always be turbulent. Viscosity is the property of fluid, which is responsible for orderliness and steady flow. Surface tension. Surface tension is the property of a liquid by virtue of which its free surface behaves as a stretched elastic membrane so as to occupy the minimum surface area. The force of surface tension is defined as the force per unit length on an imaginary line drawn on the free surface of the liquid, which is perpendicular to its length and tangentially to the liquid surface. T is equal to F by L. A very thin film of liquid near its free surface having thickness equal to the molecular range is called its surface film. Surface energy and angle of contact. Surface energy is defined as the amount of work done in increasing the surface area of its surface film by unity. Surface energy is equal to work done divided by increase in area. Its SI unit is joule per meter square. Consider a surface film of surface tension T. F is the external force applied on the wire AB in the outward direction so as to increase the surface area of the film. Then, the surface energy of the film is given by. We know that S is equal to W upon delta A. This gives the result of S is equal to T. This shows that the surface energy of a liquid is numerically equal to the surface tension of the liquid. The angle of contact between a solid surface and a liquid is defined as the angle made by the tangent drawn to the free surface of the liquid at the point of contact with the solid surface in contact with liquid. It is represented by theta and depends on cleanliness of the solid surface, nature of the solid surface and liquid, and medium above the free surface. Phenomena based on surface tension. A needle can float on water. The end of a glass rod becomes rounded on heating. Small drops of mercury are spherical burr, large ones are flat. Spraying results in cooling. Camphor dances on water. Did you know? The greater the viscosity, the less easy it is for the fluid to flow and the more sticky it feels. Some insects are able to walk on the surface of water because their weight is balanced by the surface tension of the water. There is always an excess of pressure on the concave side of a curved liquid, surface over the pressure on its convex side due to surface tension. Summary. Let us summarize what we have learned. Liquid has definite size, but a gas expands to fill any closed vessel containing it. Thrust exerted by a liquid is the force exerted by the liquid perpendicular to the surface of the liquid in contact. Pascal's law states that if some pressure is applied on an enclosed fluid, it gets equally transmitted in all directions. Hydrostatic pressure is the pressure exerted by a liquid at rest. A streamline is a line drawn such that at each point its direction is the direction of the fluid velocity at that point. Bernoulli's theorem states that when an ideal fluid flows in a streamlined motion from one point to another, then at every point of its path, the total energy per unit volume remains constant. Torricelli's theorem states that the speed through which a liquid is discharged through a small hole at a certain depth is same as the speed of body falling from rest from an unequal height. Surface tension is the property of a liquid by virtue of which its free surface behaves as a stretched elastic membrane so as to occupy the minimum surface area.